Yes.
All right, so I'm here to talk about moving target TESScut, and I'm from the Mikulski Archive for Space Telescopes at MAST. So before we really get into moving target TESScut, let's talk about what TESScut is. So TESS is the Transiting Exoplanet Survey Satellite. There's a lot of interesting things to say about it, but I'll just talk about the parts that are relevant to this talk. So it has a 24 by 96 degree field of view, which is enormous. It's like a whole strip of the sky, and it's divided into 16 CCDs, and each CCD is 2048 by 2048. So these are large images. It produces light curves, target pixel files, and full frame images. And it produces one full frame image. So a full frame image is that image of the entire sky, all 16 CCDs, every 10 minutes. In the initial year of operation, it was 30 minutes, but now it's down to 10 minutes. So this is a lot of data. And that's great for science, but it means that it takes up a lot of space. And step one for a lot of analysis done on these FFIs, because they are so large and cover such a large part of the sky, is cutting out the sections of interest around specific stars and objects. And so TESScut was designed as an easy way to get those cutouts from an entire sector of FFIs, so that scientists wouldn't have to keep reinventing the wheel when we as the archive could do that first step for you. So the TESScut ecosystem is actually not, it's actually two interlocking pieces of software. So at base, there's AstroCut, which has all of the underlying cutout functionality. This is a Python package. It's available it's on GitHub. It's open source. You can install it with PyPy. Anyone can install it locally. If you have your files locally, you can use it. And it doesn't just include cutouts for TESS now, it has more general cutout functionality. So it really is a more general purpose astronomical cutout piece of software. Then TESScut is built on top of that. So it's a URL-based web service that runs AstroCut on STScI servers. So this is the part that allows you, the user, to not have to get all of those FFIs yourself and to just ask us for your cutout. We do the cutout using the same software you would do if you were doing it on your own computer on our servers near the data, and then just return the data. And then on top of that, we've written a Python wrapper in the AstroQuery package to allow easy access to the TESScut web service directly from Python. So AstroQuery is a Python package that contains access to a whole bunch of different archives, and we added TESScut to that so that it makes it easier to put it within your Python workflows if you use Python. But you don't have to use Python. You can just use the URL-based web service from the language of your choice for the browser. So moving target TESScut. So moving target TESScut provides all of this same functionality, but for solar system moving targets like asteroids and comets that don't have a fixed RA index. Everything I just told you about is all based on this one specific RA index location. Even if you're searching by tick ID, even if you're searching by object name, it all fundamentally goes back to a single point in the sky that we can then find in every FFI that covers it. Whereas moving targets are more complicated. They move through time, so we have to care about where the target was in relationship to an image at the specific time that image was taken. So we've done that. And what's available for named moving targets. So these are targets that have an object name or ID recognized by the JPL Horizons Ephemerides service. And then once you have that, it's very similar to using sort of regular moving, non-moving target TESScut. You go to the main page. It's still stsci.edu/TESScut, and then where it used to just be one form, now you can choose object versus moving target. So if you click on moving target, you get this form where you can write in your target name here. I've written in the asteroid Eleonora. You can then if you hit, you can choose your size. And then if you hit this button, refresh sectors, you'll get a list of the sectors. So Eleonora crosses the test path in sector 6 and sector 23. And then you can hit this large orange download FFI cutout button, and you will get a zip file. It's always a zip file. And then within that zip file will be one FITS file per sector. And the FITS files are target pixel files, and they're target pixel files that are for the original non-moving target TESScut. The target pixel files are designed to be as close to the same as the mission target pixels as possible. That is still true, but there are a couple of differences based on the fact that it's a moving target, and we still want to provide enough information for you to connect all of your cutouts back to the original files if you need to. So that's the GUI. It's easy to use. It's very similar if you've used regular moving target TESScut. There is also an API. So here I'm going to go through the API, and then at the end of this, we'll actually dig into that file so I can show you what it looks like and what are some of the differences between it and your standard target pixel file. So the base URL is still, as I said, mast.stsci.edu/TESScut. And then there are two important endpoints. They're moving target sector and moving target astrocut. So these are the moving target equivalents of the TESScut sector and astrocut endpoints. So the sector query works a lot like the regular TESScut sector query, but because the target moves, it may appear on more than one CCD per sector. TESS looks at the same spot on the sky for its entire sector, which is about a month of observations. And so if you're looking at a particular RAN deck, it will only appear on one CCD per sector. But of course, a moving target can move between images. So here is target Stichius, and I've shown the request URL. So it's pretty simple. You just say sector !, object ID equals the name. And that is a pretty quick call. And so then if we look at what it outputs, it's the same thing that would be output. We've got this sector, the results, a list of sector names with also the sector camera and CCD split up. This one only appears in one sector. So the astrocut query, this is really the important query. This gives you the data you want. So it's similar to the regular TESScut query, but instead of taking an RAN deck, you take a target name or ID. And again, it's possible to get more than one result per sector depending on the target's trajectory. And the return cutout will only contain the time cadences when the target is in the field of view. It's not necessarily going to have an entry for every single FFI in the sector, just the ones where the target is in the field of view. So this is a longer call, so I'm not going to do it live here. But it's, again, you just give it these object ID X and Y, and I forgot to give it the sector 6, even though it was supposed to have it. That's fun. So then that, again, it always is a zip file. So I open the zip file, I extract all the files, and then here, so this is actually from a call I did before, which did have the sector as part of it. So there's only one because I specifically requested sector 6. So here's our file. So if we open it up, we can see that the number of cadences, wow, I'm finding all of these typos. The number of time cadences when Eleonora, I did this on Eleonora, is in view, is 359. So there's probably about, this is sector 6, so there's going to be about 12 to 1300 cadences in the sector, but there's only 360 where Eleonora is in view. So here I'm going into that cutout. The second extension is a data table that has a bunch of columns, including flux, that has the actual file cutouts. And so here I have animated it. And so you can see that the background stars are moving, and then Eleonora, this large blot in the middle, is always the cutout is centered on it. Now you can see it moving around a bit, and this is because we don't do any resampling. So you get we figure out based on the JPL ephemeride service what pixel the center of the object is, and then cut out around that pixel. But we don't do any resampling to make sure that the center of the object is always in the center of the center pixel. So the center of the object will move around in that central pixel. And so this is where it really starts to differ from a traditional TESS mission target pixel file, because we've added a little more information to help understand what data has been used in this cutout. So the first thing is the third extension is the aperture extension. And for traditional target pixel files, they just, it has the pixels that go into it. So for a cutout that we produce, that's just the rectangle. But for moving target cutouts, it's the entire FFI, where all of the pixels that went into any cutout are highlighted in white here. It's just ones and zeros. So you can see the path of the target across the full frame image, and you can see, you know, what pixels are going in, not to each individual cutout, but to the set of all of them. Also, that extension has the original full frame image WCS, and that's important because there are a couple of extra data columns. So there's the FFI file. All of our target pixel files from TESScut have this, so you can determine exactly what file those pixels came from. Moving target ones additionally have the target X and Y. So this is based on the cutout space. So it's where within that central pixel is the center of the target. So this can be used if you want to, you know, further align your images on that moving target. But then there's also this target RA and target deck. So these, in combination with the FFI WCS, can be used to determine exactly what pixel location on the original FFI has the moving target in it for that cadence. And then you can use that if you need to figure out which pixels went into your cutout. So we're just going to close that file. So TESScut AstroQuery interface for moving targets. This is coming soon. Stay tuned. It's going to be great. So the last thing I want to talk about is moving target TESScut for arbitrary paths. So all of this that I've talked about up till now depends on you, the user, knowing, having the target you're looking at having a designation that JPL Horizons understands. But maybe you are checking something new. You just have a set of ephemerides and you want to go from there. So you can do that. You can only do it using the API, and you use a combination of regular non-moving TESScut and direct AstroCut usage. And the user must first convert the ephemerides into a path. So this is part of the reason we're not doing this, is that it is up to the user to figure out what the RA and deck at every given moment is, and then you put that into a table-like object that has a column called time containing AstroPy time objects and position containing AstroPy sky coordinate objects. And you also need to know what sector camera CCD, so basically what FFI footprint. And you can use our regular TESS sector tools combined with these positions to determine that. So once you have all that information, I'm going to lead you through what you do. So here is just an input table. I've actually, this is also the asteroid Eleonora. I just took its path and turned it into the right kind of table. And so we know it's in sector 6, camera 1, CCD1. So the first thing to do is to retrieve the WCS object for the relevant CCD. We have a specific endpoint for that. And then we can use an AstroCut function, path to footprints, to get a list of the cutouts to make. And then we can use, I'm going to use the TESScut class in AstroQuery to retrieve those cutouts, but you could use any way you wanted. You could use the GUI, you could use the HTTP endpoints. So this is another endpoint. It's FFI WCS. You give it the sector camera CCD, and it returns the WCS as a string. So here I'm reading it into the AstroPy WCS object. And I will point out that you need this relax equals true, because this is not a linear WCS at all. It has a lot of SIP coefficients. And so it's important to have this relax equals true to get the true WCS and make the correct conversions from RANDEC to pixel space. So then we can use this function in AstroCut, and you can install AstroCut easily using PyPy. And then this will give us, so it's telling us what should be the central coordinate and what should be this the size, the shape, the X and Y coordinates for these. So you don't have to determine it yourself. And then I'm not going to do this because, again, this is a long call, but I do want to point out that these footprints are returned. Each one is the arguments just as this TESScut download cutout wants to see it. So you can directly send it, just point to it. And you will want to specify the sector, or else it will do it for all the sectors possible. And then you get your results. So then comes the most important part, and this is where we take those standard TESScuts files and turn them and center them instead on the moving target. So you can give it a target name. This is optional. I called it my asteroid, but it's really, again, Eleonora. And the other thing you want to give it is this FFI WCS. This is, again, optional, but if you want to have that third extension that shows you the path across the FFI, you need it. Although, of course, you can always recreate any of this by using that FFI WCS endpoint again. So then we get the output file. And if we open it, we can do the same thing. And so here is the video again. And of course, this one looks remarkably like the first one I did because I was actually secretly using Eleonora asteroid. So that's it. Here's the important links. Moving target TESScut can be accessed by the regular TESScut. There's docs. Keep an eye on MAST AstroQuery and Twitter. We will announce it when you can get moving target TESScut there. And there is also AstroCut docs that include information on how to install and use it. And you can find me. And after this, we've got about 8 minutes for questions. But after this, I will be in the STScI Zoom room. So if you want to talk more, feel free. So, questions?